Calc students, Coach H here with video number 3 of 3 about your Chapter 3 test review. So in this video, we'll cover the final few problems on your review, problems 21 through 26. The first thing that I want you to notice about all of these problems is that they do have an asterisk beside them. So remember, these will appear on the calculator part of your test. Again, mentioned this in the last video, but as you are kind of preparing for that test, you will take the non-calculator part first. You want to plan about 30 minutes to take that. Remember, it will involve graphing logarithmic and exponential functions. It will involve condensing and expanding logarithmic expressions and some solving of logarithmic and exponential functions. All right. Then you'll want to budget about 15 minutes for the calculator part of your test, which will involve solving exponential logarithmic functions using your graphing calculator to find that final answer. And then also our problems here involving our interest rate formulas and our exponential growth decay formulas. All right, so make sure you know those formulas, okay? Let's review those real quick. A couple formulas that are going to be really good for you to know are when it's compounding n times a year, the amount of money we're going to make is going to be our principal, and then 1 plus our rate as a decimal divided by the number of times it's going to compound per year raised to the n times t power, where again n is the number of times it's going to compound per year and t is our time in years. All right, be careful of that, in years. All right, then we also, if things are compounded continuously, we want to think about our PERT formula, okay? So principal times the exponential number, natural number, raised to the r times t. R is our rate represented as a decimal. T is time, again in years. One comment from the quizzes that I graded last week, be very careful in switching the percentage to a decimal. A lot of you made some pretty simple mistakes in that. All right, the other formulas that we want to think about, right? Exponential growth. So y is equal to a times e to the bx. And basically, this is our initial amount is A, right? X is some time, whatever is in the context of the problem. B is our growth rate. Notice that it is a positive value. And then we have exponential decay, right? Basically the same function. The only difference is B is negative, all right? So those are some formulas that you want to be aware of. You're going to see us use those here in the rest of this video. All right, let's get going with things. So let's start out with problem number 21. You invest $3,500 in a 24-month CD that pays 2.5% annual interest compounded monthly. Let's take a note of that. That's going to tell us what formula we're using. And they want to know how much money we will have when this CD matures in 2 years. All right. First off, Coach H would tell you if you can find a CD right now that pays 2.5% annual interest, you're probably pretty lucky. CD rates are pretty low. All right. Anyway. So let's go ahead. This is compounded monthly, right? So we're using our formula. It involves being compounded n number of times per year. So we're going to have our principal amount, which is $3,500, 1 plus our interest rate, which is 2.5%. So when I convert that to a decimal, it's 0.025, right? Move that decimal point 2 places to the left, divided by a number of times it is compounded per year. In this case, we're compounded monthly, so it will compound 12 times per year. And then we're going to raise this to the number of times it compounds per year times the number of years, so 12 times 2, okay? We are just going to type this all into our calculator, right? I'm not going to walk through that in this video. You can practice with that, but if you type things in correctly, you should end up with $3,679.26. All right, so pretty simple there. All right, 22, a little bit different here. It says how much money should a parent invest in an account that pays 2.75% annual interest compounded quarterly? Let's make note of that. Right? If the parent would like to have $5,000 in 10 years when the child graduates high school, right? So the question here is involving the principal amount. How much money should we start with, right? We're kind of solving for this part of the formula up in 21, right? So we know they want to end with $5,000. Oops. Now, just pretend that's an equal sign. Ignore that parenthesis, right? Equals our principal amount, and then 1 plus our interest rate, 0.0275. This is compounded quarterly, so it's divided by 4. And this is raised to the 4 times 10. Right, compounded 4 times a year and 10 years. And so again, I just want to solve for this algebraically first. So to solve for P, we're going to end up with 5,000 divided by 1 plus 0.0275 divided by 4 to the 40th power. Pretty simple to type into your calculator. Again, I'm going to trust that you can do that at this point. And that's going to tell us what our principal value is, which is going to be approximately, when we type that all out, $3,801.44. All right. So that is problem number 22. Again, know those interest rate formulas and how to utilize those. All right. So let's move on to 23. 23, you decide to invest $12,000 into a CD at Titan Bank where your interest is compounded continuously. Your financial advisor expects that your investment will double in 5 years in this CD. Question is, what is the annual interest rate for this CD? All right. So this is our PERT formula. Compounded continuously. We want our investment to double in 5 years. So if it doubles, that means we're going to end up with $24,000, right? Our initial amount was $12,000. We don't know what our rate is. We know we want it to double in 5 years, so we end up with 5R. So we need to solve this for R. This is going to require us to rewrite this as a logarithmic statement, right? So divide both sides by 12,000 first, and then we'll rewrite it as a logarithm. So we end up with the natural log of 2 is equal to 5R. So now I'm just going to divide both sides by 5. We'll move up over here. So I end up with the natural log of 2 divided by 5 is my interest rate. And when type that in your calculator, and you are going to come up approximately with 13.9%. Right? I should write it as I have it written here. 86%. That's how I'm basing my next problem off of. All right. So there's my interest rate. In part B, they're asking us how much will this CD be worth in 2 years, right? So now we know the interest rate. So my amount is going to be equal to that principal, $12,000. We know that it is 0.1386% interest rate. And we are going to multiply this by 5 years. All right, so just type that right into our calculator, and this would be worth approximately $15,833.16. All right. All right. Moving on. Question number 24. All right. So in this problem, they're giving us, I want to recognize that as an exponential decay problem. Right. We're seeing that exponential decay formula. I know it is decay because of the negative sign right there. All right. So they're just seeing how well you know your information here. All right. So what does everything represent? Right. Well, Y is representing our population. And important for us to get context here, in millions, right, after T years. Okay. All right, 7.8, what is that representing? All right, that is our initial population of Bulgaria. Now, important to remember that is represented in millions. There were not 7.8 people in Bulgaria in the year 2000. All right. And then our next value here, this is our rate of decay. Right, this is an exponential decay problem. So that's the rate at which Bulgaria's population is decreasing from year to year. And then T is representing our time in years. And again, get context in here specifically since the year 2000, right? Which none of you were born in the year 2000. I remember it greatly. People were worried prior to 2000 about Y2K. You have no clue what that is, but good memory for Coach H. All right. And then part B, find the population in 2015, right? We're going to use that formula and we're just going to plug in 15 for T. So we're going to end up with Y is equal to 7.8 E to the negative 0.00949 and multiply that by 15. And that will be approximately, when you type that into your calculator, 6.8. Now, if you leave it as 6.8 on your test, I will take a point off because you were telling me there are 6.8 people in Bulgaria in the year 2015. I don't think that is correct because it would be 16.8 million. So get that context in there. All right, that brings us to the fourth and final page of our review. Let's go on to problem number 25, all right? So, talk about our good old city of Papillion in 2000, which ironically is the year that Coach H moved to Papillion. But in this problem, we want to write a model for the population growth of Papillion, but we have no idea what the growth rate is, right? So we need to figure out what R is first. But we know a few things here, right? We know in 2010 the population had grown, so I know my rate is going to be positive to 18,894. So I can use that number as my amount, right? My Y value, my exponential growth formula. Initial value, $16,363. E, I don't know what R is, right? But I know that if the year 2000 is representing T equals 0, then 2010 is 10 years later, so 10R. And now we just need to, or excuse me, 10R, trying to find my rate. Now we just need to solve for R. Again, let's do things algebraically first. So we're going to end up with 18,894 divided by 16,363, and this is going to be equal to e to the 10r. Now I'm going to rewrite this as a logarithmic function, so the natural log of 18,894 divided by 16,363, and that's going to be equal to 10r, but let's just go ahead and divide this all by 10 to get r by itself. And so when we do that, we're going to end up with a rate of approximately 0.014. So that means the city of Papillion from 2000 to 2010 grew at a rate of 1.4%. Right, but in this problem, they wanted us to write the model. So let's go back. Our model would be y is equal to 16,363 e to the 0.014 t. Right, and we could use that model to make predictions about the population of this city of Papillion. All right, that brings us to problem number 26, the final one on our review. Let's get excited. All right. So again, dealing with some exponential growth problems, and then we're going to do a little comparison, get some practice with our solving. So, all right, let's start out with letter A. We want to write a model for the population growth of the United Kingdom. This is very similar to problem number 25, essentially going to do the same type of work. Right, in 2010, population of the UK, 61.2 million, right? Our initial population in the year 2000 was 59.5. E, we don't have a clue what the rate is, but we know that 10 years have passed, so 10R. Now we should be able to save ourselves a little bit of time here because we're basically solving the exact same pattern of problem as we did in problem number 25. So you can look back at the work here, there. I'm just going to cheat and skip ahead to the end result, which is going to be the natural log of 61.2 divided by 59.5, all divided by 10. And that's going to give me my rate, which in this problem is approximately, looking at my notes here, I wrote too small, 0.002817. All right. So the model, again, that's what we're being asked to actually write here. It would be y is equal to 59.5 e to the 0.002817 times t, or x. I could put an x there. It doesn't matter what the variable is. All right. But there's our model. We can see that the UK is growing, not at a great rate, but it is growing. All right, that brings us to letter B. So we want to take that model that we created in letter A, and we're trying to see when are the populations of the UK and Italy the same. All right. Now, a couple things to notice about these population growth models, right? So the UK starts with a higher population than Italy does in the year 2000. However, when we compare the growth rates, the UK is growing at a slower rate than Italy, right? So these two graphs are going to intersect at some point. So if I want to know when will their populations be the same, and all right, how many years past 2000, I'm just going to set these equations equal to each other, right? So we end up with 59.5 e to the 0.002817 t, and that's going to be equal to Italy's formula, which is 56.7 e to the 0.0045 t. All right, all these decimal values, I know, but we can do this, people. Dig in. All right, a little grit here. So now to go about solving this, I'm actually going to get all my t's on the same side, and this is going to look a little messy at first, but we're going to remember a property of exponents to help us solve this. So I'm going to divide both sides by 56.7. So 59.7 divided by 56.7. And I'm going to divide both sides by e to the UK rate. And so that's going to give me e to the Italy's rate divided by e to the UK rate. Now, the reason why I did it in this order is I remember a property of exponents that if I am dividing two exponential statements that have the same base, I can just subtract their exponents, all right? Well, Italy's growth rate was larger than the UK's, so I wanted that to be on top, so when I subtract them, I end up with a positive number, all right? So that is then going to give me 59.7 divided by 56.7, and it's going to be equal to e to the 0. Again, just subtracting these two exponents, 0.001683 t. And now I want to switch this into logarithmic form, right? And then I'm going to end up dividing by the rate, right? At this point, my work is really similar to kind of what I had up here in part A. So I know that this is going to be the natural log of 59.7 divided by 56.7. No, 59.5. Somewhere I was like somewhere along the line I made a mistake in some numbers. All right, so this is a mess right now. All right, 59.5 divided by 56.7. You guys know where we're at. Been spending too much time making these videos. I'm losing my mind. Divided by 0.001683. And that is going to equal our time. And when you type that into your calculator, you are going to get approximately 28.641, right? So this means that in what year will the population be the same? It's going to occur in the year 2028. And Then when they ask us, okay, the question, what will the population be when the populations are equal, right? Well, I'm going to take this value for t, and I can plug it into either model, right? Either what you found in part A, right? Plug 28.641 in for t to this model, or I can plug it into the equation they gave us for Italy because they're going to be the same at that point. And if you plug that in, 28.641, you type that all into your calculator, you should end up with 64.5. Once again, be careful and include context, which is million people. So in 2028, that is when their populations will be approximately equal at 64.5 million people. All right, that brings us to the end of video 3. If you have any questions, make sure you ask. But hopefully this video helps you out. All right, good work, people. We're done.